Hey everyone, this is Soumyadeep and welcome to Mystikcon. The topic of discussion today will be basics of binary exploitation. So Sazouki and I have teamed up and I'll be going over the theory part. Sazouki will be giving a practical demonstration for it. And to say a little bit about myself, my interests include Active Directory, red teaming, and of course binary exploitation. And Sazouki, for introduction, please.
Yes. So in this course, we will do after this slides, we will do three binary exploitation. The first, the first one, it will be rope, which will exploit it using read to libc technique. The second one is forma string vulnerability, which will override global linkage table for puts with our flag function. The third one will be binary that have canary protection, so we need to leak it before trying buffer overflow.
Thank you, Sazouki.
Yes,
I'll move over to the next slide.
Yeah.
So let's talk about the basics of stack buffer overflow. So what is exactly a buffer? So buffer is a data storage area in the RAM inside the computer memory. Now it can be in the stack or it may be in the heap. It is intended to hold a predefined amount of data. So a buffer has a fixed size which is assigned to it while it is being initialized. Now, if you provide executable code to a buffer that is supplied, that is as data, victim machine may be fooled into executing it. So generally, it is recommended that the stack is not executable in nature. The code will self-propagate or give attacker control over machine. So in case of buffer overflow, there may be two possible outcomes. Either we can have a self-propagating code or we can have an executable code onto the stack buffer, which when executed gives attacker control over the machine. Now, such kind of an attack can exploit any memory operation, say pointer assignment, format strings, memory allocation, and even deallocation. It can leverage function pointers, calls to library routines via offset tables. Now, let's talk about the stack buffer. Suppose we have a remote web server that contains this function. You can see that it is taking in a character pointer as an argument, *str, and it is initializing a local buffer, that is allocating a local buffer of 126 bytes reserved on the stack. And the strcpy function in this case, which is a not to be used function, will copy argument into the local buffer. We'll tell you about why it is a vulnerable function in the next slide. Now, when this function is invoked, we know a little bit about stack frames. So when this function is invoked, a new frame, that is a new stack frame, will be created with the local variables inside the function, and it will be pushed onto the stack. So this is where we have the previous stack frame, that is frame of the calling function, and we know that stack grows downwards, right? So we have the previous stack frame, and this gonna be the new stack frame. So these are the arguments to the function, that is the character str pointer. This will be the return address. Oh, sorry. So this will be the return address that is after the new function is executed, that is func is executed, the control flow will be returned to the address pointed to by the return address pointer. Then we have the SFP or the stack frame pointer that points to the previous stack, that is points to the stack of the calling function, that is a pointer to the previous frame. And then we have the local variables of the current function, say the buffer that is of 126 bytes. Now memory that is pointed to by the str, if we see strcpy function, the memory that is pointed to by the str will be copied into the stack that is in the local variable buffer, which is of size 126 bytes. Now the thing is, strcpy is that strcpy will not check whether the string at str contains fewer than 126 characters. So what we can do is that we can supply a string that is higher than 126 bytes, and if there is not the state of art protections like that of canary or anything applied onto the stack in order to prevent buffer overflow attacks, we can overflow the SFP, that is the stack frame pointer, as well as the arguments and the return address pointer, and then gain code execution by arbitrarily setting the return address pointer to our desired location. So it is said that if a string longer than 126 bytes is copied into the buffer, it will overwrite adjacent stack locations. So if we go to the previous slide, we see that buffer is of size 126 bytes. Then we have the SFP, that is the stack frame pointer, and then we have the return address pointer. Now, since we are supplying a string that is more than 126 bytes, it is overflowing this SFP and the return address. So you see this part is overflown, and the part that is overflown will now be interpreted as the return address. So by carefully sizing our payload, we can enter any arbitrary memory and then cause the return address pointer to jump there. Now executing the attack code. Suppose the buffer contains attacker created string. For example, *str contains a string that is received from the network as input to some network service daemon. So you see the code in here, and then the return address pointer here, and str gives the arguments. So attacker puts actual assembly instructions into the input string that is sent to the network. Example, say binary code of execv bin sh. So now in the overflow, a pointer back into the buffer will appear in the location where the system occurs. So basically, after he puts bin sh as the argument over here, and then he causes the return to go to the execv function call, and hence we have a shell on the system from the remote machine. So when the function exits, the code in the buffer will be executed, giving attacker a shell, a root shell if the victim program is SUID root. Now stack corruption Redux, let's look at how exactly the stack frame changes, or how exactly this attack is performed when we are taking a close look at the stack itself. So say we have a function int bar which has an argument value 1 and local variables value 2. It is calling a function known as foo, and this function foo is taking a pointer, a void pointer of named funcp, and it has local variables of buffer which is of size 128-bit, and it's using a vulnerable system call that is known as getS, because getS has no check on the input size. And there is a strncpy after that, which is basically copying the contents of buffer into ptr, that is most up to 8 bytes, and then we have a funcp function call there. So if we look at the stack, we see that value 1 and value 2, after the obviously after the function call has occurred, value 1 and value 2 are the arguments to the function, and then we have the funcp arguments, the return address from where the foo function has been called, the previous frame pointer, that is from where foo has been called itself, and the var pointer, that is the ptr and the buffer bof. So the most popular target in order to corrupt the stack here will be the return address pointer, and since we are providing the value 1 and value 2, we can contaminate the memory that is above the stack, that is just exactly above the stack frame, and we can cause code execution there by returning there by using the return address pointer. So now Sazouki will be explaining a demo part. I'll be closing my sharing, and I'll ask him to share the screen. Sazouki, over to you.
Sure. Thank you, brother. So, guys, hi, hello. This is Sazouki. Now we are going to make some demo. I have one binary here called this one, Pauna Gochi. I don't know why I call it that. So first, we need to check what's this binary. Is it 32-bit or 64-bit? So we put file Panganacci. We see it's 64-bit, executable, dynamically linked, and non-stripped. This one non-stripped means the function name will remain the same. Like if we have function called like flag, when we reverse it with the Ghidra, it will remain flag. But if it's stripped, this binary, it will be headache to reverse it because most of the function name will get like garbage random name. So first, I will fire up GDB to check what's the security for this binary. If I make check, we see that we don't have canary here. This canary means a random bytes put by the binary before the user input, and then it will be checked after the user input, and the program will check if this canary changed. If it changed, mean there is like we have buffer overflow. It means that the user input overflow this canary, then the program exit immediately and crash. So to prevent any overwriting the return address. Here the NX, which is deb, it's enabled, which means that we cannot like drop some shellcode in the stack and jump to it. So mean the stack, it's only readable. You cannot execute anything on the stack. This one, by its stands for position independent executable. It's mean like ASLR in binary, not in the system. It's mean like each time the binary run, each function will take different address. Like for example, in main function, when we run the binary first time, it will be like 0x1234. Next, if we run it again, it will take another different address, which would be like 0x14467 like this. So it will be hard to exploit the binary with pi enabled unless we have some leak. This 145, it's just replacing some dangerous function, maybe like with the equivalent, like replacing printf with puts, something like that. This one, relero, it's mean, are we able, if it's full, it's mean we cannot overwrite the global link table offset. So if it's partial, if it's partial, it's mean we can overwrite. This one, if it's full and we have like format string vulnerability, we cannot exploit it because we need to override the global link table. Now, after we check those security, so here, since we have NX enabled, means, as I said, stack, we cannot execute the stack. So we will use technique called read to libc. You know, guys, that the libc like hold most of all the functions that this binary needs. Like for example, the puts function, the binary will not hard-coded all the function puts from the beginning. Because if we'll do like this one, the binary maybe will have huge memory. It will be like maybe instead of like 8 mega, it will be maybe like 1 gigabyte or 2 gigabytes. So that's why it's here dynamically linked. So it share this function from libc. So like for example, system function, printf function, str copy function, all it just get it from the libc. So in this case, we will make a technique called read to libc. It means return to libc. We will try to overflow this binary and make the return address point to a function like, for example, system in libc. Okay, first to do that, we need first to reverse the binary. Let me share all desktop, share. with Ghidra. Let me first run Ghidra. Analyze the binary. We go to function. The first thing I do always, I go to the main function. Once we are here in function, we see like some if condition. If once variable once equals 0 or sleepy equals 0 and hungry equals 0, then once will be affected the value 1, then it will ask us to put our name. Then we have this gets function. If we see this gets function in any binary, directly know that is we have buffer overflow, because here as per the main Linux page it said never use gets, because gets doesn't like check the boundary of our input. Like if our the variable here it's like 20 character and we put 200 character, gets will not stop us at 20. It will continue to read all our inputs. Hence, it will result overwriting the REP. Then we have if hungry equal 1, this one some checks, printf is not happy, else is happy. I don't know what's this weird thing. So first thing to do, since we have gets here, we will try to check what's the offset of the binary to overwrite the REP. So we run again VDB.
Suzuki, sorry for the interruption, but it
Yes,
would be great if you can
sure.
make the font a little bigger.
Okay, let me check. Is it okay? Okay, like this or bigger?
Yeah, I think this is great.
This is great. Okay. So sorry guys for this one. Okay, now as I said, we need to what call this one to get the offset. First, let's try to run the program and see what it does. As we saw in Ghidra, it asks us for name, Sazouki. Then Sazouki is not happy, which of course I'm happy, not happy. So we'll try to create pattern create like 40. It will generate us like unique strings, like unique pattern. Like for example, 8 byte of A then B, 8 byte then C, so we can know exactly when the REP offset. Then we run our binary, we supply the pattern. We see here that we have segfault, but so it means we crushed the binary. But here, when we saw that the REP in 64-bit and EEP in 32-bit, it's stuck in return in main plus 32. If it is sample main, here, it's stuck here to return. Why? Like in 32-bit, when we put like bunch of characters, the EEP will be affected with like for 0x, for 1. But in this case, for 64-bit, it will not happen because the REP accept only canonic addresses. So we cannot fill it all with for 1. I think the canonic, we have only allowed to override the REP till here. Okay, so what to do to get the right offset of REP? We have the next return function that the REP will jump to in the top of the stack, which is RSP. So we'll check what's the offset, what character we have in RSP. So make XJX RSP. We get this one, which in top of our stack. Then we make pattern offset. We see it's likely this one, the offset it's 20. So we need 20 characters. Then we will override REP. Let's try to override REP with canonic address. We'll create first button create 20. We take this one, run again, it asks for name, we put this one. Now we can put what we want to be in RIP, like for example, 4 A's, A. Enter. See? Now it affected in RIP. If we add another A or like 3 or 2 for A, it will not get loaded here. It will do same as it does previously. It will stuck in red function. So now we know when what offset to override the REP. Let's start build the exploit. First, I'm using found tools to create one part. Make it bigger. From found import all. Okay. So we'll declare the process. We're gonna process our binary name. Then we start to generate the payload, which I'm using Python 3, so I need to make it in bytes times 20. Now next, what we will do, since we will do read to libc, correct? So we need to know what's the exact base address of libc. It's important. We need to know the base address for libc to calculate the exact address in libc. Like for example, the function system, it's in libc. Like it have offset like 123. The base address of libc, it's like 15000. So the address of system in libc, it will be 15000 plus the offset. It will be like 1500123. But here the problem is, since we have asalar, which means the address of libc always keep changing. If we do LDD in the binary, we see here that this one, the address of libc. If we try it again, it changed here. It was D138, now it's T35A50. And we do it again and again. So even if we try to brute force it, it will be very hard. We cannot check how many bytes. 7 bytes to brute force is not it's not easy. So we will try to leak the libc address. How are we gonna do that? First, as I told you before, we have, like for the function, this binary, we have the function puts. Okay, the binary get puts from the libc address. It's dynamically linked. It doesn't have all the puts function hard coded in the binary, as I told before. So the binary have something called linkage, global linkage table offset. Because everyone will ask how the binary will know the exact address of puts, let's say of printf in libc, and libc always keep changing, and the binary address, it's remain the same. How it will know? We have something, this one, global linkage table. It have like, imagine it's table, we have 2 columns. The first column, we have something called like printf local. Printf local, this one exists in the binary. It's called printf plt. And the other one, it's the address of plt got. It's the address of printf got. It's the address of printf in libc. So when we use printf in the binary call printf plt. Then the printf plt goes, when the binary first loaded, the linkage table, it get loaded, get all the plt function from this binary, put it in the first column, then it get the correct addresses from libc and put it in the second column. So when the binary, I will show you this one, for example, GDB, let's disassemble. Main function. See, here we have PLT, like puts PLT, gets PLT, call. This one call gets PLT. Then the gets PLT, let's disassemble this one, goes to those global linkage table offset and C gets PLT and see in the second column what's the address of gets got in the libc address. We disassemble one. See, it goes jump to gets got.plt. So what we'll need to do here, we need to take puts is like printf. It takes arguments and like it takes Sazouki and print Sazouki. We need to leak the gets, the printf or puts got, so we can calculate what's the libc base address. So to do that, we go back to our script. We need first to get puts plt equal. First, we need to make elf binary equal elf, so we can read all the symbols like from the binary. Like pound tools always do the hard work for us, and I will put check sec equal false. So each time I run the script, I will not see like an X enabled or pi disabled or something like that. Okay, so we need the puts plt. We have it here already. Equal, we call it elf dot plt. We need the plt. It's like dictionary plt the puts. Okay. Now we need to put puts. The argument for puts, we need to be the puts got, the address of puts in libc. So we need puts got. I can type equal elf dot got puts. Also, since we have this binary is the 64-bit, we need to pass, because in 64-bit we pass the arguments in register. We pass it in RDI, then the second argument like RSI, RDX, R11, toast. So we need to get the pop RDI, like pop the first argument and put it in RDI. Then we call puts, and puts will take the arguments from RDI. So to do that, I will use radar, and I will do R pop RDI. We have here the pop RDI address. Okay, so pop RDI. First, we need to convert, because you know the assembly in binary they accept little Indian addresses. Do not accept like 0x123. No, they accept like this, like 0x11, like x 44, x1, 0x2, like this in reverse order. But luckily we have pound pools do all the dirty work for us. So we make P64, since it's 64-bit the address. We can remove this leading 0. Okay, now the first thing we will do, we will make payload equal the junk, the offset to RIP. Here RIP will be anything we write here, it will be loaded in RIP. So we need first to call pop RDI. what we'll put in RDI? We will put puts GOT plus P64 puts GOT. Then we have now the puts GOT argument in pop RDI. We need to call puts PLT, the normal puts in our binary, to print the address of puts GOT, so we can get the libc address plus puts PLT, P64 puts PLT. Okay, but now we have problem. If we run this one and we get the puts GOT and the program like and terminate, it will be useless, because when we will run the binary again, the puts GOT, it will be different from the puts GOT what we got, because as I said, the libc address keep changing each time. So what we need here, we need to call the main function again. We don't have main here. We need to call the main function again, so the program is keep running. So when when we got the puts GOT printed in our screen, the program goes to main again and start over. So the libc address keeps the same because the binary is still running. So we need to get the main function, main equal elf the binary dot symbolic main. You can also do like this, object dump dash d grep main. You will get the main function here, the address, main address. But you know, I'm lazy person, so the pound tools make everything for me. Okay, so payload bytes 8 times 20 plus pop RDI. We put the puts GOT in pop RDI. Then we call puts PLT to print the puts GOT. Then we call the main function again. Let's first try check the program. So we need to send after name our payload. So p dot send line after main. We need to send our lovely payload. Print. Let's print p dot receive line. Let's see what we will receive. Finger crossed. Let's run this binary. Python 3 exploit. We got nothing. Okay, so there is another line. Should be let's print another line. Again, another line. Come on. Yeah. See? Now we have something garbage input in our screen. This one, it's the puts GOT. So we need to extract this one. Let's make p dot interactive to make it interactive, so it will not close. See this one. We need this one. This one, the puts the address of puts in libc. But wait a minute, we have problem here. We called main again, but the problem is the program doesn't call main again. And see, by the way, it's get changed, not the same, because as I told you, libc address, base address kept changing, so puts GOT keeps changing. But we have problem here that the main address doesn't return back and doesn't give us the gets function again. So let's return back to the main function in Ghidra. Let's see the code. Here we have the gets function. It's in if once equals 0, sleepy equal or sleepy equals 0, and hungry equals 0. Once equal 1. So in order to gets again, so we can proceed with our payload. Let me make it. I don't know if this font. Make this one. Property. To make it bigger for you guys. Come on. Where is the font? Where is the font? It's okay, I will just copy this one for you. Another one. So here, if once equals 0 and sleepy equals 0 and hungry equals 0, once equal 1. So this one will be 1. And to get back to the main function and call gets again, so we need either once equals 0 or both sleepy and hungry equals 0. But since we have once equal 1 and this one it was sleepy and hungry, it was 0 0. But since we make the gets function and we make our first buffer overflow, this one, the 20, both sleepy and hungry overwrite with AAA, which is different than 0. So we need somehow to affect 0 to both sleepy and hungry. Luckily, the program, I'm sorry guys, I cannot make it bigger. I don't know how to make the font here. Cannot. Anyway, luckily we have two function here. We have function called ZZ, which affect 0 to sleepy. So now we have this one. If we call this one again, this function, if we call it, then the sleepy equals 0. Now we have equals 0. Okay. Now we need also the hungry, which we have here. It's called eat. Now hungry equals 0. So now we have everything to put this one 0 and this one 0. So we can go to gets again and proceed with the buffer overflow. So we need to get the eat equal elf dot the eat called eat. Okay. And hungry equal elf dot same, what is one called ZZ. That's it. So here our payload will be the garbage, the junk to get the REP offset, then the pop RDI to puts GOT in pop RDI and pass it to puts PLT. And before calling main function, we need to call eat and hungry to make sleepy and hungry equals 0, so we can get gets again. Let's try it. So plus P64 eat plus P64 hungry plus main. Okay, so this one our payload. Eat sleepy will become 0, hungry will become 0, so we should have gets again. So if we try the binary now, see, now we can put name again. We can put our payload again here, like Sazouki. Now it exists. Exit. So once we have the leak, so first we need to get this leak to calculate the libc base address. Okay, so to get this one, we need first to get the puts, liquid puts. We put it in leak. So see. Okay, so we need to know where the puts we have it. Not this one. Also not this one. This one. Not this one. Not this one. Yeah, this one. This one, I think it's some garbage from the stock. I know this one because we have XF, 0XF, which is should be the valid puts address. So leaks leak equal. So we receive it like this format. As I told you, this one it's a little Indian format. So we need to convert it back to hex or int value. So we will use the U64. If it's 32, we use U32 to unpack U64 b.receive line. We need from this till here. We don't need this one until /n. We need this one till -1, and we need only 8 byte. So we make dot adjust 8 and fill the rest. Like if we receive only 4 bytes, we can fill of course in byte. We can fill the rest with the 000. Let's try to print leak. Now we have this one in integer. So let's try put it in hex. Now we have the what call this, the puts GOT address in libc. If we do it again and again, we'll see, guys, that it keeps changing. This one, the libc base address, this one, it keeps changing, this one. But the offset always remain the same. Each libc, as I told you, have multiple function in libc, but each function have the same offset, the same last 3 bits in the function in the libc. So if you keep do it again, it's the same offset. What's the change? Change is the libc base address, because here the base address is 46000. Then it became 000, and the puts in libc, the offset, its offset, it's 06B0. So to get the correct address for this one, we just, so our binary to get the exact address of puts. So it will just take the libc base plus this one. So it became this one plus 6B0. So it will be equal 6B0, this one. So now we have the offset of the puts. So we need to know what kind of libc this one, what kind of address. To do this one, there is some cool website here. It's called libc database search. To search the what's database, this one, we can do like this. We put the puts here. We put the offset, find. Let's try to find, yeah, and see this one, AMD 64, libc 6, 2.31-3, AMD 64. And by the way, guys, you can leak everything you want, not only puts. You can, like, for example, I will just edit my exploit code to leak. Come on. To leak, for example, gets GOT. So puts, let's get GOT. I need to know what's the offset of gets. So here it will print not puts this one, it will be gets GOT. Okay, let's try to run the program again. Here's the offset of gets. So let's go to check if it's the same. Sorry, gets. Where is gets? This one. So this one offset C to 0. Yeah, see, we have the same database because all belong, because each libc have its own offset. Like maybe, for example, gets C4A, I don't know. Maybe it will show us another database if it exists. No, there is no gets with the offset. So this gets, it's showing this one. So let's download this one. See, it's showing here. The system offset, it's this one, F20. Since I don't have system PLT in in this binary, I cannot leak the system. And gets, as I said, the offset, it's C20, read F40, write string PNSH, which we'll pass it later in system. It's in offset 156. So let's download this binary, this library. Copy link address. Okay. Okay. Now we got what call this? The puts GOT, and we got what's the binary, what's libc this binary using. So we go here back, we make libc equal else libc as always check sec equal false. Okay. Now we need to know. So now we need to get the system offset from this libc and the bin sh string offset from this libc. So system equal libc dot symbolic system. Then we need the bin sh equal next libc. This one for search, for string, because this one is string bin sh, not address, it's string. So search in bytes bin sh. Okay. So now we have the offset of system, the offset of bin sh. Okay. So we need to calculate the address, because the address of system, it's the offset plus the base libc, this one, the base libc, this one. So we need to calculate this one, the address. Now we have the offset of system, and we need the base. To calculate the base, since we have the leak, we have the leak here, we will, so this one, the leak, it's base libc address plus the offset of puts. So to get this one, we need to subtract offset puts, which will get it from here. Puts equal libc dot symbolic puts. Now we have puts, so to calculate being libc base, it's the leak minus the leak, which this one minus puts minus puts. So let's make some swag. Log dot info libc address x libc base. Let's see if it's correct. Okay, we have some error here. Again, sorry. Copy string. Libc base address. Libc address. No, this one is wrong. Should be 000 here. Forgot. We put here. We lick it gets. So we are subtracting gets from puts. No, I need puts. The GOT of puts. Let's put it back. Come on. Now it's correct. Now this one, the libc. See? This one, the puts GOT, and this one, the libc base address. Okay, now, since we have libc base address, we will calculate system. System, it's system plus the system offset, which we put it here, plus the libc base. Then binsh plus libc base. Okay. Then our second payload one equals, since we got back to the main function, a times 20 plus. So we need to put binsh as argument in system. So system binsh. So we need to pop RDI plus P64 binsh plus P64 system. Then P dot send line after name payload 1. Then P dot interactive to see if we got shell. Finger crossed. ID, and we got shell. Who am I? Let me put some swag. Log dot info gamma system address plus str x system. We do the same thing to binsh. Okay. Give me shell. Okay. Sazouki ID. Okay. Now we have shell. So that's it for this one. Now my friend will continue the sites. The what call this one? The slides.
Thank you, Suzuki. You can stop the screening.
Yes,
Thank
done.
you. Just present the slides in a moment. Is my slide visible?
Yes, it's visible.
Thank you, thank you. So yeah, so we saw that the first attack vector was using the return address pointer, in which we were setting the uh, stack frames above the current executing stack frame to point to a dangerous library function, say /bin/sh, and the return address was being overflowed by the address of the system. So we'll change the return address to point to the attacker code, and after the function returns, control is transferred back to the attack code. And or we can also do something. We can change the control flow to return to libc, that is, use existing instructions in the code segment such as system or exec, etc. at the attack code. So what are exactly the issues with buffer overflow? That is what we can do if we have a buffer overflow vulnerability. So the first thing is that executable attack code is stored on the stack inside the buffer that contains the attacker string. But the stack memory is supposed to contain only data but non-executable. Next, for the basic attack, overflow portion of the buffer must contain correct address of attack code in the ret position, that is in the return address pointer. The value in the ret position must point to the beginning of attack assembly code in the buffer. Otherwise, all applications will crash with segmentation violation. And the last constraint is that the attacker must be able to correctly guess in which stack position his buffer will be. That is, he must have to calculate the buffer offset will be when the function is being called. The problem is no range checking. If we have proper range checking in case of buffers, there will be no such vulnerability like buffer overflow in our system. So strcpy functions like strcpy gettys and others does not check the input size. So the simple instruction strcpy buff, str will copy the content pointed to by str into the buffer variable. It will simply copy memory contents into the buffer starting from the address pointed to by str until a null character is encountered, ignoring the size of the area that is allocated to buff. The library functions, C library functions that are unsafe are strcpy, strcat, gettys, scanf, scanf if there is no format string specified, and printf. Does range check help? So in this case, we'll be using strncpy in order to specify the range, that is the size up to which we should copy the attacker pointed string to the stack buffer. If strncpy is used instead of strcpy, no more than n characters as specified will be copied from *src to start destination. Programmer has to supply the right value of n. Now we'll talk about a potential overflow vulnerability that occurred in Apache 1.3 in a particular file known as htpassword.c. So the overall structure of the file where the vulnerable code existed was somewhere like strcpy record comma user, strcat record comma colon, and strcat record comma cpw. So can we see the vulnerability here? So it copies the username pointed by user into the buffer record and then appends a colon and hashed password cpw. So if we see that strcpy is being used, that means in the attacker controlled parameter user, we can enter a string of size that is greater than the size of record. In this case, we are overflowing the buffer. So once the fix was published, we can see that instead of strcpy, strncpy is used, and the particular size parameter was mentioned so that there cannot be a buffer overflow in this case. Attack 2, the second attack vector, using pointer variables. So if we have a pointer variable in the local stack, we can change the function pointer to point to the attacker controlled code. So any memory, it necessarily need not be in the stack, can be modified by the statement that stores the value into the compromised pointer. So what we do is that during the overflow, we will change the location pointed to by the pointer to an attacker controlled code by changing the value of the global function pointer in the global offset table. So strncpy ptr buff commit, that is just copying 8 bytes of value from buff into ptr and then setting star ptr equals 0. And the third attack vector, that is the frame pointer. In this case, we will change the caller's saved frame pointer. Until now, we were changing the return address pointer. Now, we will take control of the previous frame pointer. So, we'll change the caller's saved frame pointer to point to attack controlled memory, so that the caller's return address will be read from this memory. So, by changing the PFP or the frame pointer, we are no longer in control of the return address of the current frame, but we are redirecting the frame. Once the function exits, it will change its frame to an attacker controlled frame where there is a new return address there. So basically, the attacker can redirect the function flow to his anywhere. He can redirect the function flow to his attack controlled code. Next up, format strings in C. Sazouki will be giving a demo of format strings very soon after the theory part is covered. So proper use of format strings looks something like this. Say we have a integer variable foo that is storing the value 1, 2, 3, 4, and printf foo equals %d, which is an integer format string, in decimal %x, which is a hexadecimal format string, and the arguments applied are foo and foo again. So this will print foo equals 1, 2, 3, 4 in decimal and 4d2 in hex. This is a perfect use of format strings. Now, sloppy use of format string. It often happens that we don't want to use a %s or %x, for example, and we directly write printf buff saying that what change it will happen. It is just printing out the string itself. So character buff 13 equals hello world and printf buff, it is a wrong coding practice. It should have been used printf %s buff, although both of them will give the same output. But however, if this buff is attacker controlled, then it might lead to serious consequences. If the buffer contains a format symbol starting with %, so suppose buffer contains itself a format symbol starting with % instead of regular strings that are generally supplied, the location pointed to by the printf's internal stack pointer. So instead of the printf was expecting a string, instead it got a format string itself. So it will try and take the argument that is just above the format string on top of the stack, and it will be interpreted as an argument to printf. This can be exploited to move printf's internal stack pointer. So writing stack with format strings. So the %n format symbol tells printf to write the number of characters that have been printed. So printf overflow this %n, ampersand myvar. So basically what it will do is that it will take the length of the string that has been printed until %10 occurs. So in this case, length of overflow this, which is 14, and it will write this 14 into the variable that has been supplied as an argument. So argument of printf is interpreted as the destination address. So this writes 14 into myvar itself. Now, what if in this case printf does not have an argument? So if it does not have an argument, that means that it does not have such address on top of the stack exactly above the string. That means whatever is there, whatever address is present on top of the stack just after the string will be written 14. So car buff 16 equals overflow this %n and simply printf buff. What it will do is that stack location pointed to by printf's internal stack pointer will be interpreted as the address into which the number of characters will be written. So whatever address will be present just above the printf's internal stack pointer will be written into 16. Now using %n to mung the return address. So this is the stack format of the stack when the previous function was being called, and this is the attacker string that contains %n, and this is the attack code. So this portion contains enough %symbols to advance printf's internal stack pointer. So using %n, %n, %n multiple times, what we are doing is that we are trying to advance the internal stack pointer pointed to by the string, and buffer with attacker supplied input string. This is the buffer with the attacker supplied input string. Now number of characters in the attack string must be equal to what? So we'll see that exactly the number of characters or the number of %n's or format symbols that must be specified what should it correspond to? Using this red, that is the return address pointer, will override the location under the stack pointer with the ret address. So printf buffer will write the number of characters in attack string into ret, and then we'll have the return address pointer again to return the execution to this particular address. Now C has a very concise way of writing multiple symbols. Instead of doing %n, %n 100 times, we can do is that %mx. So it will print exactly m bytes, taking them from the stack. If attack code contains enough %mx so that the total length is equal to the most significant byte of the address of the stack code, the address of the attack code, this byte will be written into red. Repeat 3 times, that is 4%n in total, to write into red1, red2, and red3, and red plus 4. So in this case, by using 4%n's, we are replacing the entire return address pointer with the address of the attack code. Now Sazouki will be giving a short demo on format. Over to you, Sazouki.
Thank you, brother.
I'll just stop my sharing. Yeah, you can share now.
Okay, so guys, we'll do now one format string binary. So we'll choose this one called an array. So try this one. This one I get it from CTF, array CTF. Try good, then hit exit. So if we try a bunch of buffer overflow here, we supply long input, nothing will do. But if we try to put some format string, we see some random hex here. Those random hex, it's from the stack. So it's mean, as my friend said, we have printf format string vulnerability attack here. So let's reverse it with Gidra first. I have it already here. In functions, always I go to the main function. Let me copy this one. Okay, this one main function, we have it called response function here. So let's see what's this response. Copy this one. So it puts, as we saw, puts how are you finding ACTF F gets. So here we don't have the buffer overflow because F gets, it reads 200 in hex, which is 516 bytes from the std input and put it in the local 20-hour input. So we don't have buffer overflow here. And then it said, I'm glad you. Then we have here printf local C, 20C, our variable, without specifying the format string, like should be 20S, should be like this. So here we have problem in format string vulnerability. So what we're gonna do, first when I start to learn this one format string, I said, okay, I will get some value from the stack. Then what's the impact? What I can I do? But then I read that if we specify /n, we can write something in address which we choose. So for example, imagine if we have system address in our binary, and then we have another function, like for example, we have now printf, and here we have puts. Imagine if we override the address of puts GOT with the address of system, if we have. So it will have, we have system, and like imagine here be message, we will have shell. So in this case, we'll try to override, since we have puts after the printf, we'll try to override the puts GOT, as I explained it before, with, I think we have function here called flaggy. This function flaggy is from CTF, which just do system cat flag.txt. So we'll try to override flaggy address in puts GOT. So to do that, first we need to check what's the offset of our input. If we put like this, we run the binary and put like 4 A's, then bunch of format string. Let's see in which position we can see our binary in the stack. We see here like 1, 2, 3, 4. C for 1, for 1, for 1 each, which is A. So our input, it's in the position 4 in the stack. So let's try to build the exploit. Call it format.py, like always, compound import start. Okay, then p equal process the binary, then we need the elf to get the function address from the binary. Let's put checkpoints, check true. Then we need to override the puts GOT with what call this one, the flaggy function. So we need first to get the flag function, elf.scene flaggy. Then the puts GOT, we need to put GOT because as we saw before GDB, if we disassemble the function response, we see here our printf, the vulnerability here, then the puts PLT is called. and if we see puts plt, it jump to this address, which is puts GOT. So we need to override this address with flaggy address, with this address. Example, with this address, flaggy with this address. So we get the flag address, then puts GOT equal elf dot symbolic. Puts are not symbolic. GOT. Then let bound tools do the heavy work. So the payload will be this one. It's predefined function for mastering vulnerability payloads. FM forma str payload in the position 4, which we saw our input in position 4. Then we want to replace the puts GOT with flag. Let's try to see how the payload looks like. Python 3 forma. See, this one the payload will look like. Imagine I will write this one by one. So that's why the bound tools always let bound tools do the heavy work. So now let's try to send our payload. So pip.send line after our payload p.enter active. Let's try this one now. See, I just created here a flag called Sazouki cat flag, because in flaggy, as we saw, it's catting flag.txt, and here the flag.txt I put Sazouki. Let's put something else like echo 1, 2, 3, 4, 5, 6, 7. We added to flag. Let's try to run the binary again, the exploit again. We will see Sazouki 1, 2, 3, 4. So we override the puts GOT with the flag function. So still have slides, my brother?
Yes,
check.
we have just one single slide. You can continue. We'll show it at the end.
Okay, sure. The other binary, it's this one. Yes. What's your name? It's called for my name. Like, let's put Sazouki. Do you want to pet my canary? So it's clear that we have canary here. No. Then it exists. Exit. So let's try. Let's first check the security of this binary. We have NX enabled. Now we have canary. So we need to leak the canary before putting the buffer overflow. So let's check the binary. I have it here. We have flag. Keep in mind, we have this one. We need to jump on this one. And we have in main function, we call two other function, anger and say hi. Let's see say hi. Say hi here. We have gets, which clearly we have buffer overflow here. And we have printf for mastering. So we need to leak the canary here. So Let's go to GDB. Let's run it. Let's first make breakpoint. Sample. Say hi before the canary. Check. Here we have here the canary. Here it check EBP minus 11. 0C it's 11 or 12. No, 12. And XOR, make XOR. If it's 0, it jump equal. Say hi. It exists. It exit. It's leave. If not, it will jump to stuck check fail, which means that we smash the stack and we overwrite the canary value. So let's make breakpoint here to check what's the canary. Run. Let's try put bunch of P. We have here some kind of output from the stack. If I put no, we hit the breakpoint. We check the canary. The canary it's 0EB FB77, but here we don't have it yet. So we need to continue till we leak the canary. So since the canary I saw it here, it's checking ABB minus 0 minus 12. So I'll start from 10, 11, 12 to check if the canary exists in this location. So we'll run it again. To access in the 11 position in the stack, no need to put a bunch of P. You can access like this directly. Like for example, $10 P. You will see we have this one. Here now, let's check the canary. The canary it's 6B D8000. No, it's not the same. So let's try to run again. Let's try in the position 11. We have this one. No. Canary it's A6 886B, which is the same as this one. So we have the canary, it's in position 11. So we have leaked the canary. Then we have another input which use gets. So we can override the EEP to point to the flag function. So we will do, let's start our exploit. Canary .py from bound port deploy. So the payload will be, first we need to send first 11 P to get the canary. Let's check. Yeah, so send after name. So P dot send line after name. We need to send in bytes 11 $P. Print P dot. Check if we get it. Python 3 canary. Yeah, we have it. This one. So second one, the canary will be starting from here. So canary equal split. We'll split the string. Why don't split this one? We'll take the first. This one the first, the 0. This one the second one. We'll take this one from position. This one, it's empty, so position from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 characters. So 1 to 11. Let's try to print canary. Here are bytes. So we have the canary here. Correct. Perfect. We need first to convert the canary to integer. Canary equal int canary 16. Because the canary it's in hex in base 16, so we need to convert it to an integer, so we can send it back to the binary. So now we need to check where is the canary offset. GDB, yes. Pattern create 28. Run. If you put this one, we have stack check fail. So it means we overwrite the canary already. So let's try to create another pattern create 26. Run. See, in 26 character we overwrite the canary. So let's try 24. Run, no, here. It's normal. So in 24, it's safe. We didn't touch the canary. Let's try 25 to make it sure. Run, no. Let's try to add a. So 25 also, no problem. So the canary starting from 26. So the payload will be A25 plus B32. Since this one it's 32 binary. 32, so P32 canary plus, let's create pattern create 20. Now we need to know when we can override the EIP plus P dot send line payload. Let's try now. It crashed. Let's crash it in 61616164. So it's mean AAAD. But then create 20. So in AAD it crashed here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So here AAD. So the offset it would be 9. Second, this one 4, 5, 6, 7, 8, 9, 10, 11, 12. So here. So 12 to override the EIP. Let's try P times 12 plus, let's try EIP. Of course, in bytes. Now we override with AAA. So now we need just to call the flag function, which we saw it in Ghidra. This one. This one. We have the flag function here, which will cut the flag. So we need to call it. So flag equal. Sorry, flag. So this one, the EIP. So to flag. Let's make p.interactive and run it again. Now we have the flag, which is Sazouki 123, and we managed to bypass the canary and the NX enabled. Thank you for watching. Now, brother, I will give you
Sure, we have
to
the
share the screen.
ending slides.
Yes.
So we will briefly talk about what there can be other targets of memory corruption exploits. There can be configuration parameters such as directory names that confine remotely invoked programs to certain a certain portion of the server's file system. There can also be pointers to names of system programs. For example, if we can replace the name of a harmless script with an interactive shell. This is not exactly the same as we are talking with return to libc, because in case of return to libc, we are not replacing the names, but we are instead changing the function parameter or flows of the return address pointer to some address, say the system or say execv address that is present inside the libc or the binary itself. Branch conditions in input validation code can also be used in case of memory corruption exploits. Thank you, and may you have a happy Merry Christmas.